This question says find the difference quotient of f of x equals x squared minus 5. That is, find f of x plus h minus f of x over h not equal to 0. Be sure to simplify. So this expression right here, f of x plus h minus f of x over h, is the difference quotient, and that's the calculation that we're going to do using the function x squared minus 5. We're going to find the difference quotient using a three-step process. First, I'll find this part of the numerator, which is f of x plus h. Everywhere I see an x, I'm going to change that x to x plus h. So that means that I would have x plus h squared minus 5, and I want to simplify this. X plus h squared is x plus h times x plus h minus 5. And I'll multiply that out to get x times xh. Sorry, that's x squared plus xh plus xh plus h squared minus 5. Then I'll combine like terms to get x squared plus 2xh plus h squared minus 5. And that's as far as I can go with the first part. So then I'm going to do the second step, which is to calculate the entire numerator. Now I've already calculated the first part of the numerator above. That's the f of x plus h. And then I want to subtract f of x. So I'm going to copy down my work from before for the first part. And then I want to subtract f of x. I want to minus x squared minus 5. And notice I put the parentheses around f of x because I want to make sure I subtract that whole function. So I'll distribute that negative to both the terms in the parentheses, which gives me x squared plus 2xh plus h squared minus 5 minus x squared plus 5. Now I can combine some like terms, and these like terms are going to end up canceling each other out. I have x squared and negative x squared minus 5 and plus 5. So since those terms are like terms but also opposites, they cancel each other out, and I'm left with 2xh plus h squared. The final step is for me to calculate the entire difference quotient. So that would be f of x plus h minus f of x over h. So we have the whole numerator that we just calculated divided by h. And all the terms in the numerator have an h in it. So we'll be able to simplify 2xh over h plus h squared over h. The h's cancel, and one h cancels here. So I'm left with 2x plus h. So the difference quotient for the function f of x equals x squared minus 5 is 2x plus h. Find the difference quotient of f. That is, find f of x plus h minus f of x over h for h not equal to 0 for the following function. Be sure to simplify. Our function is f of x equals 10 over x squared. So I'm going to write out what the difference quotient formula is. That's f of x plus h minus f of x over h. For our function, for the first part, I'll replace the x with x plus h, so it becomes 10 over x plus h squared minus 10 over x squared over h. We're going to simplify this using a clearing fractions method. So what I want to do is I want to simplify the complex fractions that I have. A complex fraction is when you have a smaller fraction inside this bigger fraction. So I want to eliminate those smaller fractions to simplify this expression. So to do that, I will multiply by a fraction, and that fraction is going to be created by using the common denominator between these smaller fractions. So I'm going to multiply the numerator by x squared times x plus h squared, and the same thing gets multiplied by the denominator so that I can keep this expression balanced. Then what I'm going to do is distribute to the numerator that common denominator to each term. Let me write out what that would look like. We would have 10 over x plus h squared times x plus h squared minus 10 over x squared times x plus h squared. There's no distributing to do in the denominator since there's only one term, h, in the denominator. So I'll just write out that multiplication in the denominator. So I've distributed that common denominator to each term, and now the clearing fraction should happen. It should cancel out the denominators of those little fractions. So in the first term, we have a denominator of x plus h squared, which is going to cancel with the x plus h squared here, and that leaves me with a 10x squared. In the second term, we have a denominator of x squared, which cancels with the x squared, and we're left with minus 10 times x plus h squared. And that's over that same denominator that we had earlier, h times x squared times x plus h squared. We will continue to simplify, and what I want to do now is to simplify this x plus h squared. So that's 10x squared minus 10 times x plus h times x plus h over h x squared x plus h. And I made a mistake here, left off a squared. Okay, so that leaves me with 10x squared minus 10 x squared plus xh plus xh plus h squared over h x squared times x plus h squared. And I can combine these like terms together, which would give me 10x squared minus 10 times x squared plus 2xh plus h squared over that denominator. And now I'm going to distribute this negative 10 to all the terms in the parenthesis. That's 10x squared minus 10x squared minus 20xh minus 10h squared over hx squared times x plus h squared So now we're going to be able to cancel out these like terms of positive 10x squared and negative 10x squared. So those cancel, leaving me with negative 20 xh minus 10h squared over hx squared times x plus h squared. And then finally, because we have factors of h in the numerator and h in the denominator, we'll be able to cancel those out. And we're left with negative 20x minus 10h over x squared times x plus h squared. So the difference quotient for 10 over x squared is negative 20x minus 10h over x squared times x plus h squared. Find the difference quotient of f. That is, find f of x plus h minus f of x over h. H of x not equal to 0 for the following function. Be sure to fully simplify. So our function is f of x equals square root 10x, and we're going to find the difference quotient, which is f of x plus h minus f of x over h. So the difference quotient for this function would be square root of 10 times x plus h minus square root of 10x over h. So to simplify this expression, we're going to use a method called rationalizing, and we're going to rationalize the numerator. So to rationalize, we're going to multiply by a fraction, and we're going to multiply by the conjugate of the numerator. So that conjugate would be square root of 10 times x plus h plus square root of 10x. So we used a plus here as the conjugate because we have a minus here in the original. I'm going to multiply by that same thing in the denominator so that the expression stays balanced. This is multiplying by 1. Multiplying by 1 doesn't change the expression. So in the numerator, I'll need to multiply out those expressions. So I'm going to take it slow and do square root of 10 times x plus h times square root of 10 times x plus h. Then I'll have a plus square root of 10x times square root of 10 times x plus h. Then I'll have a minus square root of 10x times square root of 10 times x plus h. Minus square root of 10x times square root of 10x. Okay, so just to make it a little bit more clear what I was multiplying there, I was multiplying these two terms together to create this term. I multiplied these two terms together to create this term. These two terms to create this term. And then finally, I multiplied these two terms together to create this term. So that's what I have in the numerator. In the denominator, for all of that, in the denominator, I am not going to multiply anything out. I'm going to leave it in its factored form. So I have h times square root of 10 times x plus h plus 10, square root of 10x. So now I have a lot of simplifying to do. In the middle here I have a positive square root of 10x times square root of 10 times x plus h, and then a negative square root of 10x times square root of 10 times x plus h. So these two terms in the middle will cancel each other out. When I multiply the first terms, in the first term, when I do that multiplication, I have 10 times 10, which is 10 squared, and x plus h times x plus h, which is x plus h squared, inside the square root. And the same thing happens, or a similar thing happens, in the last term. That's square root of 10x times square root of 10x. That's 10 squared, square root of 10 squared, and square root of x squared. Once again, I'm leaving the denominator in its factored form. So because we have perfect squares underneath these radicals, we're going to be able to simplify. So the square root of 10 squared will be 10, and then the square root of x plus h squared will be x plus h. And then we have square root of 10 squared again, so we have another 10. And square root of x squared would give me x. My denominator is staying the same. H times square root of 10 times x plus h plus square root of 10x. In the numerator, I can use the distributive property to simplify those parentheses. So that's 10x plus 10h minus 10x. We have h times 10 plus x plus h plus square root of 10x in the denominator. And in the numerator, we have a plus 10x and a minus 10x, which cancel each other out. So I have 10h in the numerator and h times square root of 10 times x plus h plus square root of 10x. And we can now cancel out these factors of h that we have in the numerator and denominator, which gives me 10 over the square root of 10 times x plus h plus the square root of 10x. And one last thing that I could do to simplify this, which I don't typically do, but I just want to demonstrate it because I've seen it a bunch of different places, is both of these radicals in the denominator have square root of 10. So I could factor out that square root of 10 and be left with square root of x plus h plus square root of x. And then we typically don't like to have the square root of a value in the denominator. So I could rationalize that by multiplying by square root of 10 over square root of 10. So let me kind of treat these separately. So I'm not changing the second fraction here with the radicals, but if I multiply to this first one, square root of 10 over square root of 10, in the numerator I would have 10 square root of 10, and in the denominator that would multiply to be square root of 100. And square root of 100 is 10. And then I'm able to cancel out these 10s here. So if I put that back together, I would have square root of 10 over square root of x plus h plus square root of x. And that's my difference quotient for square root of 10x. Using the given graph of the function, find the following: the intercepts, the domain and range, intervals on which it is increasing, decreasing, or constant, and whether it's even, odd, or neither. So let's start with the intercepts. An x-intercept is where the graph crosses or touches the x-axis. So we have our x-axis here, and the graph touches the x-axis, crosses the x-axis, touches the x-axis in these places. So we have x-intercepts at negative pi, 0, and pi. And we also have y-intercepts. A y-intercept is where the graph crosses or touches the y-axis. The y-axis is this vertical axis, and the graph does cross that y-axis at 0. So we do have a y-intercept at 0. Then we're going to find the domain and range and write that domain and range in interval notation. So when I find domain and range from a graph, I like to use a ruler or a pencil. And I'm going to hold my ruler vertically. And the reason why I'm holding it vertically is because my ruler is going to be going across that x scale, the x-axis, from left to right. So I'm looking for when is the first time my ruler hits the graph, and that's going to tell me the start of my domain. So the first time my vertical pencil or my vertical ruler hits the graph will be at negative pi. So my domain starts at negative pi. And then I want to decide if that point is included in the graph or not included. Because this one has a filled in dot at that point, it's included, and I'll use a bracket on that point. As I move my ruler from left to right, I can see that I'm continuing to hit the graph all along the way. So all of these x values will also be included in my domain until I get to this point. That's the last time my ruler will hit the graph. So my domain will stop at pi. And pi is also included in the domain. I'm going to do the same thing for the range, but I'm going to hold my ruler horizontally, going from bottom to top. So I'm holding it horizontally because my ruler will be going across that y scale. So for the range, the first time that my pencil hits the graph will be at this point right here, which has a y value of -3. So that's where my range will start. That point is on the graph, so I'll use a bracket to include that in the range. And as I continue from bottom to top, I can see that all of these y values are part of the graph. The last time I hit the graph will be at this y value of +3. So that's when my range will stop. That value is also included. The next part says to find intervals for which the graph is increasing, decreasing, or constant. So what I like to do with this is I like to trace the graph from left to right. As I'm tracing, I'm taking note of whether the y values are increasing or decreasing. So starting the furthest left, my y values are decreasing. So let me make note of that. That's decreasing here. And then I'm going to change colors because at this value right here, the y values are now increasing as I trace from left to right. So let me label these as increasing. And then the y values are decreasing. And now I want to label the intervals. When they're asking for intervals, we're talking about the x intervals. So we want to see when this interval starts, which is at negative pi, and this interval stops, which is at negative pi over 2. And that will be an interval that is decreasing from negative pi to negative pi over 2. Then the next interval is increasing, and we've already seen that that starts at negative pi and that ends at pi over 2. So we can say that our graph is increasing, starting at negative pi over 2 to pi over 2. And this final interval started at pi over 2 and ends at pi, and we said that that interval is decreasing. So I'm going to add that on to this section here, pi over 2 to pi, and that interval is decreasing. Now some books will write the interval notation for these as negative pi with a bracket to negative pi over 2, union with pi over 2 to pi. And then for the increasing interval, you might write it as negative pi over 2 to pi over 2 with brackets instead of parentheses. So this is dependent on how the definition is worded for that particular book. So if you use the word open interval in the definition, you would write it this way with parentheses. And if you don't use the terminology open interval, you could include the endpoints as in this way of writing it. So pay attention to the convention that your book follows as to which way to write those intervals. Our final part, we want to determine whether this function is even, odd, or neither. Let me erase my markings and we can talk about what even, odd means. For a function to be even, it needs to have y-axis symmetry. So the y-axis is the vertical axis. And to have y-axis symmetry means that we need a mirror image on either side of that y-axis. So if we have a point on one side of the y-axis, we would have a mirror image of that point on the other side of the y-axis. So if we have xy, we would have a mirror of that point, negative xy, with the opposite x values but the same y values. You can see here I have this point, pi over 2, 3, and I don't have a mirror image of that point over the y-axis, so we do not have even, this function is not even, and it doesn't have y-axis symmetry. For a function to be odd, you would have to have origin symmetry. So for origin symmetry, you want to have a mirror image over the origin where the x and y-axis cross each other. So for the origin symmetry, if you have a point, for instance xy, you would have a mirror image of that point across the origin. That point would have the opposite x value and the opposite y value. So looking at a few of these points, I've got pi over 2, 3. I have the opposite of that, which is negative pi over 2, negative 3. Opposite of both the x and y coordinates. I have the same thing with pi and negative pi. And as I'm looking at this piece of the graph, I have a mirror image of that over the origin in that opposite quadrant. So this function is an odd function. Determine whether the graph below is that of a function by using the vertical line test. If it is, use the graph to find its domain, range, intercepts, any symmetry with respect to the x, y, and origin. So we're going to start with the determining if this is a function using the vertical line test. So the vertical line test says that we draw vertical lines and we're taking a look at how many times these vertical lines cross the graph. So as I draw a few vertical lines, I'm noticing that these vertical lines only cross the graph once. So this is a function. It passes the vertical line test. The definition of a function is that every x has exactly one y, and because we're crossing in exactly one place, that means we have exactly one y value for every x. So this is a function. And now that we know it's a function, we want to find the domain and range. So I like to use a ruler or my pencil held vertically to find the domain. So I'm going to use this ruler and hold it vertically. And what I want to do is move across the graph from left to right. I'm holding this ruler vertically because it's going across the x-axis and the domain are the x values. So as I go from left to right, I'm looking to see when's the first time my ruler hits the graph, and that's starting at negative pi. So my domain starts at negative pi. And that point is included in the graph. So I'm going to use a bracket on that negative pi. And as I sweep from left to right, my ruler is still hitting the graph. So all of these values will be included in the domain, but we will stop right here at pi. That's the last time that the ruler will hit the graph. So my domain is from negative pi to pi. Then we're going to hold our ruler horizontally to find the range. If I hold it horizontally and go from bottom to top, I'm running along the y-axis, and the range are the y values. So as I go from bottom to top, the first time my ruler hits the graph would be right here, and that's marked at -1. So my range will start at -1. I'm putting a bracket because that point is on the graph. And then I can mark the last time that my ruler hits would be here at +1. So my range is from -1 to 1. Next, I'll look for the intercepts. X-intercepts are where my graph crosses or touches the x-axis. So right here is an x-intercept, and here, and here. So my x-intercepts are at negative pi, 0, and pi. Y-intercepts are where the graph crosses or touches the y-axis. So that would be right here at 0. And then I'm looking for any symmetry with respect to the x-axis, y-axis, or origin. So for x-axis symmetry, X-axis symmetry is we're looking for a mirror image across your x-axis. So looking for a mirror image on the top and the bottom. We do not have a mirror image. Y-axis symmetry, you have your vertical axis, which is the y-axis, and we're looking for a mirror image on the left and right of that y-axis. We don't have that. And for origin symmetry, the origin is 0, 0 right here. And we're looking for a mirror image in opposite quadrants. And we do have a mirror image in opposite quadrants. So this graph would have origin symmetry.